Hello, this is Rohan-Paul. Very welcome to my machine learning and deep learning YouTube channel. Let's get started. Hey everyone, so today I'll be doing a deep neural network with PyTorch, and the focus of this video is the fundamental flows and concepts of PyTorch when building a base model in deep neural network. And I'll be using the famous dataset FMNIST, FashionMNIST for this project. Let's get started. So FashionMNIST dataset consists of a training set of 60,000 examples and a test set of 10,000 examples. And each example is a 28 by 28 grayscale image associated with a label from 10 classes. So that means each image is 28 pixel in height and 28 pixel in width for a total of 784 pixels. And actually, FashionMNIST is a little bit more challenging classification problem than the previously well-known MNIST dataset. And top results in FashionMNIST regularly achieve 90 to 95% with convolutional neural network model. And on the dataset, let's just summarize what we know about the dataset already before starting any of our work. That is, we know that the images are all pre-segmented. For example, each image contains a single item of clothing, and the images all have the same square size of 28 by 28 pixel, and that the images are all grayscale. And we also know that there are 10 classes, and that classes are represented as unique integers starting from 1 up to 10. And as a first step, I'm importing all the libraries and all the standard ones. So for this project, because I'll be using PyTorch, and hence I am importing torch.nn module, which is one of the most fundamental module in PyTorch. And I'm also including data set and data loader. This will be very important for generating the batches of data to input to the model. Then I am importing Torch Vision. So this Torch Vision module has many most popular dataset in the computer vision world saved in PyTorch core library itself. So I can just import the necessary dataset from Torch Vision. And yeah, and then the transform, that's another module within the Torch Vision to transform the dataset immediately after importing it, and NumPy, of course. So quickly check out the Torch Vision's documentation. So this is the official documentation of Torch Vision.dataset. And if I go to the FMNIST here, let me quickly check where FMNIST is here. On the right side, yes, FashionMNIST. All right, so this is the official documentation, and it details each of the parameters. So I have the first one as torchvision.datasets.fashionMNIST. This takes these parameters. The first one is a root, which actually denotes a root directory of dataset where FashionMNIST dataset will be residing. And so when I'm downloading this dataset or pulling this dataset from Torch Vision, this folder will host that pool data. And if I already have this dataset already here before downloading, then of course it will not download. And that is mentioned very clearly here. The download equal to true. If it is true, downloads the dataset from the internet and puts it in root directory. If dataset is already downloaded, it is not downloaded again. And train, because this dataset will have both the train set and the test set. So when I want to include only the train set, I have to pass this parameter, which is a Boolean parameter. So if true, creates dataset from training.pt, otherwise from test.pt. And transform, this is another parameter. It takes a function or transform that takes in a PIL image, Python image library image, and returns a transformed version. We will see what it does when we get into the code. And all right, with that, I think I'm ready to start off. So first, quickly check whenever you are working with PyTorch or TensorFlow, etc. It's very important to check their versions and also because these codes mostly will be using your machine's GPU either locally or in the cloud, and that means you have to make the versions of Torch or TensorFlow or whatever library you're using compatible with the CUDA you have in your machine. So quickly just print version of them. Oh, that torch dot. Torch. Oh, I did not run this cell. Let's just run this cell. Okay, my torch is 171. That does not look good. I needed to have my torch vision at 110.1. Let me fix that quickly. I think I just need to change the Python interpreter here. So I was using Python 3.8.10. I actually want to use 3.9.10 and then restart my notebook and then run all again. All right, now I got the Torch version as 1.10.1 and the CUDA, compatible CUDA is CU113. Also, just quickly print Torch Vision version. Torch Vision dot. Yeah, that 0112 makes sense. And I'm just going to decide some my directory structure. So I always name my root input directory as this root input dataset directory. Input dataset. Okay. I always name it like this because sometime I'll be running this entire notebook, the entire project in local machine, and sometime I'll be running it in Google Colab or sometime in Kaggle notebook as well. So wherever I run it, initially I just need to change one single line here and mention my corresponding directory, and then the whole notebook will run just seamlessly, smoothly based on that. So I always declare my input root directory as a variable, and later when running in Colab, I can just, so this is for my local machine. Now, if I want to run it in Colab, same directory will refer to my Colab session storage or G drive storage that I will mention later. For now, that I'll mention later. And now time to get the data with Torch Vision. Torch Vision datasets.fa FMNIST, and it takes my root. The first one is the directory. That would be root input directory dataset, and download equal to true. So it does not. So when it finds the data already, it will not download. Otherwise, it will download. Train equal to true. I'm just including the train data now. It started downloading. It will take maybe only a couple of minutes. And in the meantime, I am just, okay, let it download. In the meantime, I'm just trying to read the one of the data that it just got downloaded. So FMNIST, let's just read the number 10th data. So it has already finished downloading, cleared the output. Yes, so if you print it like this, it will clearly show that what exactly the 10th element is, and it is a PIL image formatted data. And Yeah, so that's what it is. It is a Python image library. Now, if you want to check the actually display the image, a couple of lines more you have to do, because each of these contains a whole image tensor. So I have to get that tensor and from these element. So let's do image. It will give me two of them on the image tensor and also the label, which is an integer, equal to FMNIST 10. So this will return image. This FMNIST 10 is actually a tuple with a pillow image and also the integer integer label of that image. Right. Yes, so image size is 28 by 28 as expected. Now also print the label. Label is 0 for this one, and now just I want to display the image, and for that I'm using matplotlib.plt.imshow, and I just browse the image here, and that's my image. So this is just one piece of clothing. Like I said, that the whole FMNIST dataset is each of the image here one piece of clothing in grayscale format of 10 by 10 of 28 by 28. Now quickly see that here, while I was downloading this image, I did not make use of transform parameter at all. Now without transform, the torch vision.dataset function mostly returns pillow image. So if you want tensor to be returned, that is a PyTorch tensor, you do need to pass in a transform to convert the image to a tensor. Let's do that quickly so that we can be clear that what I'm saying here. So I'm just going to download the same line here. I can just copy from here. So I'm pulling the dataset from torchvision.datasets.fashionMNIST, but now this time I will give a transform parameter here. Transform will take transforms. Remember, I already have imported these transforms from Torch Vision. Let's quickly check this one. From Torch Vision, import transforms. And transforms take a lot of gives me a lot of functions to transform the dataset actually. So here I'm going to just make use of .to tensor. This will convert the data to a PyTorch tensor, converts a PIL image or numpy.ndarray to tensor. This transform does not support torch scripts. Converts a PIL image or numpy ndarray of height by width by channel in the range of 0 to 255 to a torch.float tensor of shape C channel by height by width in the range 0 to 1 if the PIL image belongs to one of the models L, LA, PEI, RGB. Okay, so here our model definitely belongs to RGB class, or if the numpy ndarray has dtype np.unsigned integer 8. In other cases, tensors are returned without scaling. Okay, looks all good. Let's just run it. Yeah, it did not download the dataset again because I already have the dataset, but now I have the FMNIST as a tensor. Let's check that quickly. So now if I'm going to print the same thing that I did previously, FMNIST 10. Let's see what it gives. And it gives me a tensor. See the difference? Previously, when I printed it here, without the use of the transform parameter, I got a pure PIL image here, a tuple. But now I'm getting a pure three-dimensional tensor, and this is a PyTorch tensor. Okay, let's clear the cell output, and now to just quickly check out a few more things from here. Let's do image1 equal to FMNIST. Because this was a three-dimensional tensor, let's get the 10th element 0 0 and image1. Okay, that's a tensor. Now I am actually going to view it. So I'm just using the same thing. I am show and passing to it img1, and it gives me the same image that I got previously here. All right, makes sense. Let's move ahead. All right, so that was just for checking the transform parameter, but I'm going to delete these cells because I am going to go ahead running this project by pulling the data without the transform, so that we can understand everything from first principle. Oh, all right. All right, I deleted those cells. Now, okay, so now that I have my FMNIST data, so let's get the train images and train image targets. Data. Similarly, I'm getting the target train image targets. Targets. And now let's quickly check out all these variables shapes. Let me just get this code. Print train image up, train image shape, train images.shp. Similarly, I'm going to do for train image, okay, train images size as well. And that would be size. And now train target shape. Train image targets. Okay. Okay, let's keep it shape. And similarly, train target size. Run the, okay, why did I get train images not defined? Okay, so train images not defined. Let's see. Oops, very sorry, I misspelled the word here. That would be targets, yes. All right, so I have the image shape of the train images 60,000 by 28 by 28. This is expected. Size also the same, 60,000, 28, 28. And the targets, they are single vector. So they are all just a single integer values for each of the 10 classes of targets, and that's why it's a vector of 60,000 elements, and each of them represent one of the 10 classes. All right, now let's go for the next cell. Okay, now I have the kind of understanding of the overall shape and size of the data. So now check any random single image from the train image data set. Okay, I think we already did that here. Yeah, okay. Now then I am going to plot random samples of 10 images for all the 10 possible classes. So to start the plot, I'm setting both the row and column to be 10, so it will be a 10 by 10 plots. I can just take the length of the target variable, train targets dot, I have to get unique numbers from them. And then, sorry, 10. Creating a subplot. Column and fixed size. Fixed size will take 10 by 10. Here the AX can be either a single axis object or an array of axis object if more than one subplot was created. So for this particular case, my AX variable is a 10 by 10 tuple, something like this. Indeed, if I put ax.shape, that is, if I print ax.shape, it should give me, if I print like something like this, it should give me that 10 by 10 tuple. All right. Now, for the actual plotting, let's start the looping. Iterating through the ax variable for variable class and row value. I'm enumerating over ax. So when you enumerate over over a variable in Python, it actually gives you two loop variables. The first variable is a count of the current iteration, and the second variable is the value of the item at the current iteration. So here ax is the variable over which I'm looping, so over which I'm enumerating. So it will give me two looping variable, count and value. So let's first do label x row. Label x row. Here I will be using a NumPy function called np.where. Let me write the code and then I will explain it. np.where, and then I'm passing a condition. My condition is train image targets equal to label class. Let's take the 0th of that. And so what this code is doing is that a label x row is an array of indices corresponding to a given class where this condition is valid, that is train image targets equal to label class, and np.where makes sure of that. So np.where will return me an array, and I am selecting the very first element from that. Note that in this code, I'm fetching the 0th index as the output of np.where condition, as it has a length of 1. And it contains an array of all the indices where the target value, that is train image targets this variable, is equal to the label class. And okay, so after these, I just want to also print the label x so that while running the code, I can actually see what's coming here. Rows equal to label x row. All right, and now so again, before moving on, I think I should make clear on this np.where thing. So np.where, it outputs two possible things. The first one is it gives me an nd array, and that is n-dimensional array or a tuple of n-dimensional array if both x and y are specified. The output array contains elements of X where condition is true and elements from Y elsewhere. And if only condition is given to np.where, which is the case here, that is, I'm not passing separately X and Y, I'm only passing a condition which will return me a boolean. In that case, np.where will return me a tuple. The first element of the tuple is where the actual value of conditions dot non-zero, and the second element of the tuple will be the indices where the condition is true. Let's quickly take an example to understand this. Let me copy a code from somewhere that I didn't. Okay, so let's check out this. So what I'm doing, so A is an array, two-dimensional array, and B is output from np.where, where A is less than 4. Now if I print B, let's see what I get. Yes, so np.where gave me a tuple with two elements. The first one is an array with 0, 0, 0 value, and the second one is where the indices where this condition is true. That is, I have 0, 1, 2. That's indices of A where this condition is valid. All right, so that's enough about np.where. Let's go back to my code. And now what I'll do is loop through 10 times to fill the columns of a given row. For plot cell in. So I'm looping through row values here. Row value. Remember, our row value is coming from here. Row value. Plot. Cell.grid. I want to have a grid plot. No, sorry, I don't want the. I want the grid to be false actually. False, and I also want plot axis to be off. So plot cell. So see cell.a to be off. Okay, and then I want to randomly choose a value from label X row. So that would be my np.random.choice and label X row. Let's put a variable to this. Rand image index. And the next one. Finally, I'm setting the train image and the train image. I'm getting the actual images with the index value from my train images. That would be rand image index. Similarly, from train rand image index. Okay, and plot. Finally, I have to use the im show to show the image, and that would be my X. And let's keep the CMap value to gray. And at the after the loop is over, let's pollute plot.light plot plt.tight layout. Tight layout. All right, that should do. Actually, this will be subplots. Okay, now let's run this cell. Awesome. So I got these 10 by 10 images from each classes printed. And yeah, so these are the actual FMNIST data images. and this is just 10 random images from our dataset. And as you can see, this label X row, these are printed. So these got printed because of this line here. I was printing them to get the actual indices of label X row where these condition were satisfied. That is, label X row is defined like this using the np.where. All right. So now I am getting ready to. So this was kind of the only little bit of knowing the data. Now I will actually delve into the building the network, building the neural network. So basically, I will be using the torch.nn module. The torch.nn module provides many classes and functions to build neural networks. You can think of it as a fundamental building blocks of neural networks. Models and all kind of layers, activation function, parameter classes, etc. So the first thing for building my neural network, I would need to build a dataset generator or dataset transformer function. So this class or this function is derived from the dataset class and needs three magic function, you can say, which is init, getItem, and len. Let's start coding that, and then I will gradually explain each of these function. Class, I'm naming my these dataset generator class as dataset transformer because I'm going to do a little bit of transformation of the original dataset here. Dataset transformer, and it inherits the PyTorch dataset class. Dataset. So we already have imported dataset. Let me just make sure. Yes, torch.utils.data import dataset. This is the line. Okay. Now, the first function is init, and it will take two arrays or tensors for parameters. Train images, which is x, and train images target, which is y. So two arrays. One is x and another one is y. So def self x y, and I have to convert the input into floating point number, and why I have to convert that that I will explain after defining the function completely. So let's convert x to x.float, and this is like one of the most common thing you will see in most of the init function in neural network, that it in 99% of the cases, or probably sometime even more cases, you need to input the floating point numbers as the input values to your first layer. So x.float will do that for me. And I also need to flatten each image into 28 multiplied by 28, that is 784 numeric values, where each numeric value corresponds to a pixel value. And again, why I am doing the flattening, I will explain in detail after doing this class. So let's do that. So I'll be using x.view function here to convert to flatten this array. So my first parameter, I'm passing it to 1, which will mean that it will be inferred by PyTorch based on the other shapes that I'm mentioning. My other shapes are 28 multiplied by 28, 784. Remember, our original image here is all grayscale image, and they are of shape 28 by 28. We already checked that. So, and then I just need to, yeah, I think that's all the transformation for now. And then I can just returning self.x and self.y as xy. Okay. So that is done. Now my next function is get item. So get item function returns a sample from the dataset given an index. Um, get item, and this also takes just the index. Self.x index and self.y passing the index. And I now it is necessary to have both the model and the data on the same device. Either the CPU device of your, and by device I mean the actual hardware that you are running the entire code on. So it could be a local hardware or the machine in the cloud. So the device should, the model and the data should reside on the same device. It can be either CPU or GPU for a better processing. Data on CPU and model on GPU or vice versa will result in runtime error for sure. So I'm going to use a function called toDevice. This method will move the tensor or model to the specified device. Let's first quickly check if I have defined my device at the top. Normally, I always do that. Okay, I have not defined the device. Okay, so let's define my device first. So, yep, I should define it, I think, here itself at the very top. Or maybe not with the imports. Let's have another cell here. So my device code will be like this. It's again a very common code in PyTorch, and it's a very common convention in whether you are using PyTorch or TensorFlow to have a properly defined device. So CUDA if torch dot CUDA dot is available, ABLE, and else it will be my CPU. Okay, if CUDA, so okay, so these first CUDA will make sure the GPU of my machine is used, and otherwise if the GPU is not found or the torch.CUDA is available returns false, then my CPU will be used. All right, coming back to my dataset generator code here. Yeah, okay, so I have my X and Y defined, but now my device is defined. So now I just have to transfer these tensors to that device that I have declared at the top. So what I'm going to do, oh, 1 second. Yeah, return x.to device y.to, you can see. All right, and the last function I need is len. Len function just returns me the size of the data set. Len self. So here again, I'm just implementing the most basic form, the most simplified version of these functions. In actual world, while you are dealing with various kinds of data set, you have to customize this function in a varied ways. So to in my future videos, I will get into those details when I deal with various kinds of image dataset. But here in this video, it's just the absolute basic bare bone base model version of this. So that's what I'm doing here. Let's return just a len self dot x. That should do. All right, now create a function. I'm going to create another function that will generate a training data loader. That is, I will make use of this data transformer class. So div load data. So first I'm getting the output from the dataset transformer that I wrote previously. So let's dataset transformer, and it takes two parameters: train images and train images targets, and put these output into a variable. Let's call it train data. And now I'm going to use the second super important function inbuilt within PyTorch called data loader. Data loader, and that takes output from the previous line. So that would be train data. And I will talk about this data loader function in slightly more detail in a second. First, let's complete this line of code. It also takes a batch size. These parameters are like super duper important and also super common in any PyTorch neural network code that you can visit. Let's put it 32 and shuffle also true. Shuffle equal to true. And let's call this train loaded data and just return train loaded data. All right, now let's quickly understand this data loader function. You can I definitely recommend you to read their official documentation. So they mentioned here very beautifully here in their documentation that code for processing. Why? So the fundamental question you may ask that why do I need these dataset generator function, which will contain these init, get item, and len, and also another function for loading the data, that is a data loader function. So what the documentation says is that code for processing data samples can get messy and hard to maintain. We ideally want our dataset code to be decoupled from our model training code for better readability and modularity. PyTorch provides two data primitives, torch.utils.data.data loader that I just used in the previous function, and also this torch.utils.data.dataset that allow you to use pre-loaded data sets as well as your own data. Dataset stores the samples and their corresponding labels, and data loader wraps an iterable around the dataset to enable easy access to the samples. Okay, that's very beautifully and compactly written indeed. So basically, what data loader is, what data set is, that is this one, torch.utils.data.dataset that I used here in this function. That is my whole dataset transformer actually inherits from that torch.utils.dataset. So this class is basically an abstract class representing the dataset. It allows us to treat the dataset as an object of a class rather than a set of data and labels. And then talking about the next one, that is for this is for generating the data and then for loading the data and implement all sorts of control during the load of the data. That is whether I want to put shuffle equal to true, the batch size that I want to mention, etc. And there it takes even more number of parameters. I could mention that I could make use of the parallel processing of my CPU and mention the number of threads that the data loader function should use. All these kinds of super important things. So the data loader, the torch.utils.data loader class not only allows us to iterate through the dataset in batches, but also gives us access to all these inbuilt function for, like what we just mentioned, multiprocessing, allows us to load multiple batches of data in parallel rather than loading one batch at a time, shuffling, etc. And yeah, so that's about this function. And so that was kind of the mechanism of these dataset and data loader function. But now coming back to the original question, that why I need them at all, fundamentally to understand that, note that training a deep learning model requires us to convert the data into the format that can be processed by the model. For example, the model might require images with a width of 512, a height of 512, but the data I collected contains images with a width of 1280 and a height of 720 maybe. Hence, that's kind of one of the reason that we need some way to be able to convert the available data we have into the exact format required by the model. So that's one of the reason. And then a data loader, in simple terms, is a function that iterates through all our available data and returns it in the form of batches. For example, if we have a data set of 100 images and I decide to batch the data with a size of 4, our data loader would process the data and return 25 batches instead of all of them, all of the 100 together. And each of the 25 batches will have 4 images each. And that's the reason, that's a fundamental reason that I can train a deep neural network model in any hardware machine at all, because even if you have the most powerful hardware, the most powerful GPU, like multiple V100s, multiple the super powerful NVIDIA GPU, even in that case you cannot load a 200 GB dataset into your model and train them. So data loader function makes that possible, that how I can load 200 GB, 500 GB, 1 terabyte of dataset and load them in batches and train them in batches, making the whole thing possible at all. So yeah, so that's kind of two of the main reasons that I need those dataset transformer, that is, sorry, dataset generator and data loader, and to structure them properly to have my project continue well. Now, so now I am going to make the function for starting the training using torch.nn.sequential. But before that, a quick word I just forgot to mention about the data loader, that using these mechanism for generating or loading the data can be done in many ways with pure Python from scratch, but and does not require PyTorch as such. However, using the data loader function of PyTorch will give you the complete control over, very tight control over the way that you want to load your data. For example, all this batch size, shuffle, number of CPU cores you want to use during the loading process. So this is an absolute requirement, I would say, for most of your PyTorch model. And all right, before also starting the training, I just want to go over a few more points at why I used float, why I had to convert the X input to float, and also another point that why I need float at all. Okay, let's just quickly go over that. So what is a float in Python? A float is a specific data type in Python equivalent to double in C or C++, which can hold non-integer real numbers. For instance, 8.2, 8.3, 7.5, and so on. And it is called float as in floating point numbers. And a floating point number basically is a way of representing a number with a fractional component in a computer. So coming back to the question of why do we need a numbers to be converted to float, what we did here in this step, x equal to x dot float, why we need these conversion in neural network. So from a purely theoretical perspective, from purely technical perspective of mathematics, some people may argue that you really do not need this conversion, because any number can be you can use integer instead of float in a neural network, as float can easily be represented as integer divided by k, where k is a multiplying factor. So from a purely theoretical viewpoint, this is definitely possible, but it will result in a loss of precision, since integer falls in the integer set of numbers, whereas float falls in the real number set of numbers mathematically. So converting real numbers to integer will result in high precision loss if you are using very high precision. For example, float 64. Real numbers have an uncountable infinity, whereas integers have countable infinity, and there is a well-known argument called Cantor's diagonalization argument, which proves this. And so to elaborate more on this point in the context of neural network and conversion to float, from a practical viewpoint, the most well-known activation function in neural network are sigmoid and tanh. And the main property of these activation functions are that they squash numbers to between 0 and 1 or between -1 and 1. So if you convert floating point to an integer by multiplying it with a large factor, which will result in a large number almost always, and pass it to any such function, that is any such activation function, the resulting output will always almost be either extremities, that is it will be either 1 or 0. So that's kind of the practical reason that without conversion to float, just inputting integer number to a neural network is not going to give you result at all, because you will have a big precision loss in that way. And now also the next question, that I flatten the input layer with this line x equal to x dot view, and then I passed a dimension of 28 by 28, that is 784, and kept the first dimension to be inferred from this. So how does the view work? So basically, this is how the view works. The view reshapes a tensor by stretching or squeezing its element into the shape you specify. So for example, on the leftmost upper corner here is my original tensor, just an example. It's of 3 by 4, 3 rows and 4 columns. Now with the t dot view and then passing 2 by 6, I will have 2 rows and 6 columns. And similarly, if I do t dot view 1 and then 12, I will have 12 columns and just 1 row. Similarly, I can also do t dot view 4 by 3, that is 4 columns, 3 columns. I can also do 6 by 2 and 12 by 1. In this case, I will have 12 rows and 1 column. So the return tensor shares the same data and must have the same number of elements, but may have a different size. And so this syntax, view dimension 1, dimension 2, and so on, returns a view of the same underlying information but reshaped to a tensor of shape dimension 1 into dimension 2, and so on, whatever you have after this. So that's how I did the flattening here. And now the basic question again, that why do I need to flatten the data in a neural network while processing images? So the short answer is that the preprocessed data should be good input into the model, I mean without flattening, but it needs to be in the form of one-dimensional linear vector. Regular, rectangular, or cube shapes can't be direct inputs, and this is why I need to be flattening fully connected layers. So the answer lies in getting all the information from the input vector, that is the input tensor. So unless I flatten it, so the basic reason that I had to flatten is because unless I flatten it, I will not extract all the information that is there inside the original tensor. And this is how it works. So each of these image in FMNIST has 784 elements, as in pixel, in its multidimensional array of 28 by 28. So the flattened one-dimensional array is going to have a total of 784 elements in a single one-dimensional array. By doing so, we can define the number of nodes or neurons of the input layer as well. So the input layer after flattening can now take in the image data with no problem at all into its each and every neuron. Hence, we can define the number of neurons to be exactly 784. And by doing so, a flattened one-dimensional array includes the total number of elements included in the original tensor, which was not flattened. But due to this flattening, I do not have to deal with the badge dimension at the initial input layer. So I found this great answer in this Quora explained by Professor of Physics at Belmont University, Mr. Scott Hawley. So why do we flatten the data in a neural network while processing images? So what he's saying that you don't have to flatten if you are using a CNN, that is convolutional neural network, but if you are using a regular dense or linear layers of weights, the answer is because you want to couple information that exists vertically as well as horizontally. And he pretty much explains what I just mentioned, that that the input layer, I should not lose any information from the input images, and that's why we flatten. So he explains here very well in this post in Quora. The other answers are good. Okay, okay, so say you have a batch of n monochromatic images which are R rows and C columns each. So your input matrix X has dimension of n into R into C, and let's say you want to do classification and you have M classes, so you want to output matrix Y, that is n by M. Now multiply that by an ordinary two-dimensional dense weight matrix in order to get a layer of H hidden activations. Your weights will need to have a dimension of C by H, and your resulting activation will have a dimension of N into R into H. Notice that R is still there. So R, again, it's the number of rows. So in fact, for ordinary matrix multiplication and barring CNNS, without doing something akin to flattening, you will never get rid of R. The most you can hope is an output matrix Y, that is N by R by M. So furthermore and more significantly, there is no way to couple the information across rows in X. So this is the key point, that we unless I flatten it, there is no other way to couple the information that is there vertically, that is within the rows, without flattening. So yeah, that pretty much the reason he explained very beautifully here. You should definitely go through this link in Quora. All right, now let's move ahead to do my next set of function, which is actually coding the training function. All right, so where was I previously? So we did the data loading part is done, data transformation is done, and data loading part is done. Okay, now I'm ready to do the training. So first I'm importing an optimization algorithm from torch.optim. Here I'll be using SGD. And now the function. Let's name it run model. And I'll be using nn.sequential. Let's see, sequential. And then inside it, I will pass various layers. nn.linear. First, I'm passing 28 multiply 28, and then 1000. Then I'll be using rectified linear unit. So nn.relu. Then another linear layer. And here 1000 into 10. I definitely need to do the two device thing so that my model data and original data remain in the same device, either CPU or GPU. And the loss function, it's a multi-class classification problem, hence I'll be using cross entropy loss. Loss function, cross entropy loss. Then optimizer will be my SGD. Model appeared. Parameters and learning rate, let's keep it at 0.001. And now I'll be returning my model. Then I think small spelling mistake, optimizer. Okay, model, I'll be returning loss function and also optimizer. So on the notes on why I used 1000 here and 1010 here in these last linear layer is that this whole model is a network with one hidden layer containing 1000 neurons. That's why the 1000 number here. And the output is a 10 neuron layer since there are 10 possible classes. And that's why and the last layer nn.linear has 10 here. All right, now I am going to do the function which will actually run the whole training and do the prediction and calculate the loss function. Let's call it trainer each batch because it will do the training on a batch by batch basis. It will take X, Y, the model, optimizer, and the loss function. First, I have to call the model on the batch of inputs, and I'm going to use model.train. So let's do predictions equal to model. Let's okay, model X here. X. Okay, before that, I have to do this thing. Model.train. And why how the model.train works is that it tells your model that you are in a training mode. So batch norm layers use per batch statistics and dropout layers are activated as well. And then just a prediction from the model and then compute the loss from the loss function. Loss for this batch would be equal to loss function from my input parameters, and to that I'll be passing the prediction and the ground truth. Prediction and Y. All right. Why I'm getting loss function is not defined. I have defined it here. Is there a spelling mistake? Nope. Anyway, I think it's just VS Code acting weirdly. Okay, now I also have to apply the backward function to this loss for this batch dot. I will explain what this backward function is doing in a second. So on these backward function here, first take a look at this prediction equal to model X. What this is doing is that based on the forward pass in model, then within bracket X, this compute all the gradients of model.parameters. And after this is done, then I am doing the backward. And this is after this is done, then I'm calculating the loss and then I'm doing the backward. So what backward is doing is this. Loss.backward computes the derivative of loss with respect to x for every parameter x. So for every parameter x where actually which requires grad set to true. This is how it works. So it just computes the dloss dx, this value, and these are accumulated into x.grad for every parameter x. So in pseudocode, x.grad would be equal to plus equal to dloss dx. So that was my backward function. And wait a second, let me just, okay, now I have to do the optimizer.step. Again, I will explain what this step is doing in a second. Optimizer.step, and the final one is optimizer. I have to flush out the gradients from memory before next batch of calculation. So I have to do this 0 grad. Okay, and at last I'm just return loss for this batch, and okay, I have to actually do this item thing here. All right. So on this optimizer.step, what this will do, it will just update all the parameters based on parameter.grad. So to understand that in slightly more detail, let's go over this, how the backward is working again. So recall that when initializing optimizer, you explicitly tell it what parameters of the tensor of the model it should be updating. The gradients are stored by the tensor themselves. They have a grad and requires grad attribute once you call backward function on the loss. And after computing the gradients for all tensors in the model, calling optimizer.step makes the optimizer iterate over all the parameters of the tensor it is supposed to update and use their internally stored grad to update their values. That's how the optimizer.step works. All right, I think it's better to go over a quick separate example to understand this flow of applying backward and then applying step and updating all the parameters. So I have a little script here. One second, let me copy it from somewhere that I have. All right, I got it. So this is my script. Okay, let's go over what I'm doing here. So here, this x is my original tensor defined as torch.tensor, then 1 and 2, giving its a value, and its required grad parameter or attribute is set to true. Now, if I print the original input x, it will show me original input tensor is 1, 2, requires grad equal to true. Now I am also setting a y value, which is a function of x, and let it set it as like this, that is y equal to 100 multiplied by x. And also I am doing a quick loss calculation. Loss is just y dot sum, and here the main story and the main flow of the gradient calculation and updating the gradient with backward and step. So after these loss calculation, if I directly print x.grad, that is, I directly want to access the grad attribute of x, I will get none because it has not been set yet. But then I call loss.backward, and what loss.backward does is it calculates a gradient. It computes gradients of loss with respect to all the parameters in loss that have requires grad equal to true, and I have requires grad equal to true for all the parameters. So this line will compute that gradient, and now if I print x.grad, I will get these values. It's a tensor, and then these values 100 dot 100 dot etc. And so I got the backward calculation. Now the next step, where I have to update all the parameters with these gradient calculation. So now I modify the parameter by subtracting the gradient because I'm using SGD, that is stochastic gradient descent, where I have to update the new weights by deducting the learning rate and multiplied by the gradients. So this is what I'm doing here. Optim equal to torch.optim.sgd, and I pass x as the input parameter, and learning rate is 0.001. And now if I print x, I will get this tensor after applying the SGD. And the final step is this step that I did as the final step here in this function. So like I said previously, that all step does is it iterates through all the parameters and update the parameters. So that's what I'm doing here, that optim.step, and now I'm printing x again, and now I'm getting this updated tensor with after applying the step function. So the loss.backward here sets a grad attribute of tensors which requires grad equal to true in the computational graph, of which loss is a leaf, only x in this case. Then the optimizer just iterates through the list of parameters that is a tensor it received on initialization, and everywhere where a tensor has recurse underscore grad is set to true, it subtracts the value of its gradient stored in its dot grad property, that is simply multiplied by the learning rate in case of SGD, stochastic gradient descent. And it does not need to know with respect to what loss the gradients were computed. It just wants to access the dot grad property so it can apply the SGD formula. And what is the SGD formula? This is just this, that just this, that is updated x updated weight equal to previous weight minus learning rate into x dot grad. All right, so again, just to wrap up this discussion on these modify and on these backward and step function, that when you call loss.backward, all it does is compute gradients of loss with respect to the parameters in loss that have recurse grad is set to true, and store them in parameters.grad attribute for every parameter in the tensor. And then optimizer.step updates all those parameters based on parameter.grad. I spent such a long time on these explanation of backward and step function here because it's so fundamental in PyTorch or any neural network, even when you are working with TensorFlow, to understand these steps, that is how the gradients are calculated and how the gradients are updated while the neural network is moving forward or moving backward through the layers, is extremely important. And all right, now this cell was just for example, let me delete this cell. And so I have my trainer function ready, trainer each batch. So wrap up again, what this trainer each batch function did is that it passes the batch of images through the model in the forward pass, then computes a loss on batch, then passes the weights through the backward propagation and updates them. Finally, it flushes out the memory of the gradient so that it doesn't influence how the gradient is calculated in the next pass. All right, now all my functions are ready. I think, no, I am still going to do another function called accuracy, where I will be validating my prediction by calculating the accuracy. Oh, I made a small spelling here. Model, there was a dot. It should have been here. All right, now I am going to code my evaluation function. So diff accuracy x, y, and model. So first, I will be setting my model.eval mode. Previously, while training, I set it to model.train here. So now, because I'm in the evaluation mode, I will be setting my model.eval. So basically, what this will do is that model.eval will notify all your layers that you are in eval mode. That way, batch norm or dropout layers will work in eval mode instead of training mode. So all you have to do is just model.eval. All right, now get the prediction matrix for a tensor of x images. Prediction equal to model pass x. And now compute now for the evaluation, I need to compute if the locations of the maximum in each row coincides with ground truth. And for that, first I am going to identify the argmax index corresponding to each row with prediction.max, and then I will be passing -1 to it. So max, let get max values, and argmaxes equal to. So this prediction, I'll be using prediction.max. This will return me a tuple, and I will be accessing the -1th element, argmaxes. Okay, looks all right. And now finally, I'm comparing I'm going to compare argmaxes with the ground truth through a condition called condition set up like this: argmaxes, that is, this value is equal to y. So let's do argmaxes equal to y, and let's set it to some variable is okay, now let's set it to, yeah, is correct. And finally, I'm just going to return these is correct in a list format and through my CPU device. Return CPU dot numpy dot list. All right, that should work. And now all my functions definitions are ready. So I'm now fully ready to do the actual training. So first, load my data. Training data loader. We have this function called load data, I guess. Where did I define it? Yeah, load data. Okay. So training would be load data, and then for training the model, I have to run. I have the function named as run model, so I have to run this model, this function. But let's set the output into a variable which should be model. It returns me. Let's quickly check what does it return. So my model function returns a model, loss function, and optimizer. Okay. So model and loss function optimizer equal to run model. Okay. And then the next cell, I'm going to run the all epochs. And this is the main crux of the story, that I'm going epochs by epochs and passing each epoch the batch of images. First, let's define two arrays to hold my losses and accuracies. Losses, two empty arrays. Okay. Now for epoch in range farm. Let's do, I'm going to create a list that will contain the accuracy and loss values corresponding to each batch within an epoch. So before, these losses and accuracies was for the entire run of the model for all the epochs, and now inside I'm going to create two more variables for similar parameters, that is losses and accuracies, to hold the numbers for each batch within each epoch. So LOSSES, loss in this epoch, accuracies in this epoch. Now create batches for training data by iterating through the data loader variable, that is this variable training data loader. For index, let's call index as ix, and batch in, I'm enumerating over that number, iter training data loader, x and y are my batch, and train the batch using I'll be using the function trainer each batch for training each of the batch, and store the loss value at the end of training on top of the batch as loss for this batch. Have I defined loss for this batch? No, yeah, no worries. I am going to train and then store the loss value for this batch. So let's do that. Loss for this batch would be equal to trainer each batch this function and pass this function x, y, model, optimizer, and also the loss function. And also I'm going to hold the losses in the, I'm going to update the losses in this epoch after this. So losses for this epoch, sorry, losses says yes, losses for this epoch in this epoch dot append loss for this batch. Okay, and after the above loop I have to update the epoch loss. After the above loop is done here, now store the mean loss value across all batches within an epoch. So that would be my, let's call this variable epoch loss. Epoch, I can actually name this epoch mean loss. Okay, let's skip it for now. Epoch loss would be np.array, and then within it I will pass this losses in this epoch and take the mean of it. All right, next I calculate the accuracy of the predictions at the end of training of all the batches. So that would be for ix batch in enumerate. I will be using iter and same data training data loader. xy equal to batch is correct would be equal to my accuracy function that I just what was the function name? Accuracy, yeah. Accuracy, and it takes x, y, and the model, and then updated as CCU or SCY accuracy in this. Let's use this extend function to up and pass it is correct. All right, and now epoch accuracy again. Epoch accuracy again would be the np.mean accuracy would be np.mean accuracy in this epoch. Accuracy in ch. Am I spelling it correctly? I mean, accuracy in this epoch is not defined. Where is the problem? Yeah, the spelling mistake. Accuracy in this epoch, accuracy in this epoch. Okay. Not defined because I have not run it. Or again, a spelling mistake, quickly check. Where is my accuracy function here? That is run. Let's run this function. Okay. Oh, it will take, I think, a couple of minutes because it's actually doing the training. Yeah. Okay, 9.7 seconds only. All right. Now, okay, these cell will take a couple of minutes to run because it will go through so many epochs, 5 epochs indeed. Okay, this looks good. Epoch accuracy. Oh, yeah, spelling mistake again. Extra C here. Accuracy. Okay. And my epoch accuracy is np.mean All right, now that I have the epoch loss and epoch accuracy, I can update, and after the entire loop is done, that is these two for loops, these two enumeration, I am ready to append these epoch losses and epoch accuracies to these two variables at the top that has been defined. Okay, so let's do that. Losses dot epoch loss. Similarly, erases dot epoch accuracy. Okay. I before while running the epochs, I also want to mention see actually which epoch it's running. So let's include a print statement here. The current epoch is the current epoch is see epoch. All right. Now I think I'm ready to run these training. Oh, I think I just forgot a very important thing, and that is the accuracy. Before running these accuracy function in this cell, I have to set an important thing called torch.noGrad. So that's just this at torch.noGrad. Okay, what this will do is that torch.noGrad impacts the autograd engine and deactivates it. And it will reduce the memory usage and speed up computations, but you won't be able to do back propagation, which you don't want to indeed during your evaluation stage. So torch.nograd basically just keeps the gradient calculation over the weights. That means you are not changing any weights in the specified layer, and which is what I want to do while I am doing just accuracy calculation and just evaluating. Yeah, so otherwise, apart from this evaluation, for example, just to give an example, if you are training a pre-trained model, it's okay to set torch.nograd as well on all the layers except fully connected layer or classifier layer. Okay, so I have to run from this cell again. So I'm just execute cell and below. Okay. Yes, so my training has started. The current epoch is 0. I think it will take only, yeah, it took around 10 seconds per epoch. So I think I'll be done for 5 epochs in 50 seconds, less than a minute. Okay, let's just wait here how it pans out. And after this, I also have to do a plotting to see the actual visualization of how the losses were improved on a when I was moving through the epochs. That is, at the 0 epoch, my loss will be large, and at the end of the last epoch, my loss will be much lesser. It's still running. Yeah, it just got over. Now just plot these losses so that I can actually see my losses. So yeah, epoch in p dot ing one and so on, and then plot.figure, plot.figure. Let's set fix size equal to 25. Plot dot subplot, let's leave it 121. plt dot title loss value versus epochs POC agent. Plot dot plot. Let's give it epochs, then losses. Label is equal to training loss. This because this is what is happening here. And plt.legend, also plt dot Now my next plot will be plt.subplot 122. Title, this would be my accuracy versus epochs. And plt dot. Again, this will take the epochs, epochs, and this time it will take the accuracies list. Label is equal to training accuracy. Let's do a GCA here, and GCA set y tick label. Where is y tick labels? And let's give it something like this. So, okay, I think I have it somewhere written already. Let me copy it. All right, I just copied this thing because sometimes I'd really get confused about this formatting. .0f and in percentage. Yeah, looks okay. Format x into 100 for x in plot.gca get y tick labels. Okay, this should run epochs. Spelling mistake. epochs. Okay, let's run this cell. Okay, I got x and y must have first dimensions but have shapes of 1 and 5. Okay, got it. The spelling mistake here, it should be epochs. All right, now I'm ready to plot it, but I made a mistake, and I can change it in a single line, and I have to rerun these training again. So that mistake is that while I was inputting all the batch by batch data to these my entire training, I did not scale the data. So that means my data was in the original format. I did not do the scaling or normalization of the data. So let me do that. And to correct that, to include the scaling, all you have to do is change this single line, that is x equal to x.float and then divide by 255. So here scale them. What I'm doing is scaling them to the range 0, 1 by dividing by 255. Now, why this rescaling is so important is because each digital image normally is created by a pixel with a value between 0 and 255. 0 is black and 255 is white. So rescale scales the array of the original image pixel values in the range of 0 to 1, which makes the images contribute more equally to the overall loss. Otherwise, higher pixel range image results in greater loss, and in that case a lower learning rate should be used, and lower pixel range image would require a higher learning rate. To avoid this kind of things, it's almost always important to scale the input images in the range of 0 to 1. Now let's quickly go over the scaling concept and how this affects the activation function calculation and why scaling is so important in almost all neural network modeling. So first, note the sigmoid function values formula. It is 1 divided by 1 plus e to the power minus input into weight. And this weight remains the same whether I'm scaling or not, but this input value, this is what changing. If I'm scaling, it will be much smaller value, that is between 0 and 1, and if I'm not scaling, this input will be large value. So that's where that's what I'm calculating in the table below, that on the left hand side, this is for non-scaled version of sigmoid value calculation, and on the right hand I have the scaled version of sigmoid value calculation. In both the table, the weight values remains the same. Only change is the input column. Here on the left side, I have taken the non-scaled version of the pixel value, and I have taken the maximum value of a pixel in an image, which is 255. And on the right table, I have taken the same input values but scaled. that is scaled by dividing the input pixel value by the number 255, giving me 1 for each of them. And now note the difference between how sigmoid is changing in values in the left table versus how sigmoid value is changing in the right table. So in the left table, we can see that when the weight values are more than 0.1, the sigmoid value does not change with an increasing weight value. Furthermore, the sigmoid value changed only by a very little when the weight was extremely small. The only way to change the sigmoid value is by having the weight change to a very, very, very small amount. However, on the right table, the sigmoid value considerably changed when the input value was small. The reason for this is this formula, sigmoid function, the calculation of this exponential and the mathematical implication of this. So the reason is that the exponential of a large negative value is very close to 0. And in the left hand side, our weight remains the same in both the calculation, but on the left table, our input is large. That means when I am doing this calculation 1 plus e to the power minus input into weight, this expression becomes very close to 0. While the exponential value varies when the weight is multiplied by a scaled input on the right side of the table, because here the input value are all much smaller compared to these values on the left. Here input values are all between 0 and 1. And hence, on the right table, that is when my input values are small and it is scaled, I am getting a more responsive sigmoid value changes. That is, here the sigmoid value changes when the weight changes. And that is more, these changes is more smooth during the whole calculation, because while the neural network layers will be back propagated and forward propagated and the weights will be updated, I will see a corresponding updates in the sigmoid value as well. Hence, scaling the input dataset so that it contains a much smaller range of values generally always helps in achieving a better model accuracy. So now coming back to my code, so that's why I had to do the scaling them to in the range of 0 to 1 by dividing by 255. And now let's run these entire notebook again. And the training is going through epoch by epoch. It will go over 5 epochs. I'm done with 4 of them. And let's see how this comes out. All right. Okay, the training is done. And here's my final plot. And looks pretty beautiful. So what I got is that my loss versus epochs, that clearly shows that for the first epoch the loss was really high, and then how it continually decreased over the 5 epochs. And similarly the training accuracy also increased. After the 5 epochs I got almost I think, yeah, it should be around 86% of accuracy, and that's only after 5 epochs. If I run after up to maybe 70, 80 epochs, I will definitely get much better accuracy. All right, so in this video, I implemented this base level version of PyTorch model for implementing a neural network on FMNIST dataset, and in the next video I will implement some of the hyperparameters changes and see how the accuracy improves or the losses get decreased. So in the next video I will be doing changes in the learning rate, also the batch sizes, and also using different loss optimizer function apart from SGD. So yeah, so these for this base level, this is accuracy I got, and for 5 epochs actually it looks really very good. And like I said, the FMNIST dataset has become one of the most fundamental dataset to check and test many computer vision algorithm, and it's highly solved problem by now. People in the industry regularly gets beyond 95% to 97% accuracy on FMNIST dataset by implementing neural network on it to predict the values. That pretty much wraps up this video. Stay tuned. My next few videos will all be on OpenCV, image processing, and computer vision. So if you have not subscribed yet, do subscribe. And if you have liked this video, smash the like button. See you in the next video.